The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome. Thank you for joining the Oregon Housing and Community Services Multifamily Energy Program training on effective ventilation strategies for multifamily. This is Mecca Abraham speaking now. Our presenter today is Matt Christie. Before I pass it on to him, I wanted to start off with a couple of housekeeping items. You can move on to the next slide. All right, to start off on how to use GoToWebinar. Today's webinar will be recorded and available on the program website within several days of the presentation. All attendees are currently in listen-only mode. If you'd like to ask a question, please ask the question in the chat box on the GoToWebinar panel. We'll do our best to answer questions in the order that they are received. And at the end of the training, we will open the audio line for questions. In order to participate at the discussion at that time, please enter your audio pin located in the center panel of your screen and raise your hand in the meeting panel and we can unmute you. You can also feel free to enter questions in the chat box as well. Next slide, please. All right, so as a reminder, this webinar is part of a series of trainings geared towards supporting multifamily energy program participants and multifamily professionals. We will cover topics relevant to both existing buildings and new construction projects. Just wanted to remind you on two upcoming trainings after today. On September 27th, the topic is on planning for energy efficiency upgrades. And on October 11th, we will be discussing optimizing multifamily building operations. You can register for these trainings and future trainings on our website. So I'll now pass it off to Matt Christie, who will kick off our training.
All right, thank you so much, Mecca. Appreciate it. Glad to be here. Good afternoon, everyone. Thanks for listening in. We're going to be talking about ventilation in multifamily buildings. I'm going over some of the basics and the history and the whys behind ventilation itself. We're going to be talking about specific strategies and value propositions of various ventilation methodologies, some standards and guides, and some ways that you can get some true engineering support and kind of professional methods for designing, specifying, and installing good ventilation. And then also talk about the business case for prioritizing the best systems and making the right choices for the buildings that you're consulting to or constructing or building on. And then take some time for questions at the end. So first and foremost, ventilation basics. Why do we ventilate? What's the broad picture here? The differences between mechanical and natural ventilation, and the wonderful concept of build tight and ventilate right. So start with why do we ventilate? And we ventilate for the obvious reasons. Indoor air quality and health of occupants is the primary reason here. Inside buildings, we spend about 90% of our time indoors, and inside our buildings, we build up CO2 by breathing out. We don't have enough plants inside. We build up toxins and volatile organic compounds and dander and all this stuff that we got to get out of the air in our house so we can breathe in good quality, healthy, fresh air, making lives longer, making asthma better, all those good things. And so homes need to ventilate to do that. Now, there's been a broader and deeper focus on ventilation in the last 10 to 20 years as sort of the building science revolution has come through, and we've been thinking about our buildings a little bit more critically and a little bit more thoughtfully about how we establish the indoor environment that's best for us and healthiest and most energy efficient. And what's happened over the last few decades is there's been a lot more new materials in buildings, a lot more we have formaldehyde, or we used to have formaldehyde in the way we designed and built our counters instead of just wood and nails. We have these chemicals, we have radon, we have all these things being introduced to our indoor environment that probably weren't there before in as high of a levels. We also have codes and standards pushing for health that are making this, for health and energy, that are making the need to ventilate or sort of regulating and mandating the need to regulate indoor air quality for the health of our occupants. We also have tighter buildings, which means they're not moving air in and out naturally as much as they did. Natural ventilation isn't as easily achieved. And with siting and land development, we've switched where buildings are. And so, that Dakota that's on the screen right now, that building, that probably got a lot of wind exposure and a lot of operable windows back in the day where, the air would come swooping in and out over the course of the year. These days, it's probably boarded up on all three of its sides by other buildings, blocking that wind, blocking that natural ventilation opportunity, meaning we probably have to rethink how we get fresh air indoors to the occupants. And so just like our lungs breathe in and out, push out the toxins on our out breath, and breathe in fresh air on our in breath, we have to have buildings that are doing that constantly. So let's talk a little bit about why not natural ventilation. It's because natural ventilation isn't doing it constantly. There's seasonal differences, there's diurnal differences within a day, and then there's hour to hour. Natural ventilation works because there's a pressure difference somewhere in the building, on the shell of the building to the inside, that's moving air in and out, and therefore pushing out the dirty air, the toxin-filled air, and pulling in the fresh air. And that works well and good in some situations, but when the wind stops blowing or those pressure dynamics stifle, then you lose natural ventilation. It's not happening. Or when the windows are all closed up and you're shutting down the pathways, a small pressure differential isn't enough to push in enough makeup air. So here's a chart of a sort of an annual curve of a specific building where you have this the blue that you've overventilated and underventilated. Obviously, with a standard building envelope that is pretty loose, you're getting huge degrees and variations of whether or not you're getting enough ventilation in that home based on the time of year, which is based mostly on temperature dynamics and therefore pressure dynamics. And then with a tight home, it's sort of kind of staying right in the middle there. And this chart is a nice example of how it can change in a season, but this can also change in the middle of a day. If it's 65 degrees out and there is no wind, a naturally ventilated building is not ventilating. It's just sitting, and that stale air is sitting indoors. And that causes health problems, and that causes production problems in a commercial and building, and that's what we're trying to solve. So the stack effect, everyone says that stack effect drives natural ventilation frequently in some buildings, and that's true. Stack effect is a pressure differential where air basically, you have a different temperature, you have a different pressure on the bottom of the building than at the top of the building, being pushed against the building's facade itself because of the temperature dynamics on the inside. And so air naturally ventilates in from the bottom and out to the top to some level. But what about those middle floors? Those middle floors don't get much of a stack effect. And once again, you have stale air just sitting in those homes, sitting in those apartments. And that's problematic to those that live there. And even the stack effect can kind of get shut down a little bit if you have a really tight envelope or if you have great compartmentalization going on within the building. So the building science community has come to their first ever sexy catchphrase, build tight and ventilate right. It rhymes, it's accurate, it's good for the environment, it's good for the indoor air quality. So we've been using this phrase now for about 25 years, and it will continue forever because people are pretty attached to it. It's just the right thing. Build the building tight, make a tight envelope that doesn't ventilate itself naturally. Natural ventilation kind of being the original sin of construction, right? It just so happened that our buildings were loose so air could get in and out, and we've sort of been using that as a crutch for years and years to deliver indoor air quality. Now it's time to finally recognize, nope, that's not the right way to do it. That's not actually providing indoor air quality. Let's build tight and then ventilate right, which means intentionally. Put the air where it belongs, the right air, the most quality air. So there's sort of three different methodologies for mechanical ventilation. Exhaust only, supply only, and balanced. And I'm gonna kind of walk through the differences between those three and what the dynamics are in multifamily buildings. So first off, before I get into the three different types directly is, let's talk about what the values are of good ventilation. First off, it distributes air into each of the living spaces. So you get distribution across all the living spaces where humans are residing, so they're getting air quality in each room, in each part of a building. Second, that air that they're getting is fresh, it's quality, it's breathable, it's healthy, it has all the good qualities that air has and few of the bad qualities that air has. So typically that means it's filtrated. And then third, this balance is just that those two things are kind of happening consistently, balanced in both time, that balance unit to unit, room to room, that as a system, this is happening everywhere consistently all the time. Kind of related to being distributed well, but also just this sort of ethos of doing it for everyone at the same time. So exhaust only is the one that most of us, is most common currently in new construction and most common even in buildings that have older buildings that had this done prior. And as you can see, basically you are pushing air out of your dwelling units, creating a negative pressure. That's what those minus signs are within the units in that red coloration. And then makeup air comes in from somewhere. Those are those little green arrows. So those are coming in from seams and cracks and around the windows and through the outdoor insulation, and often in from the basement coming up into the building if there is a basement, or those are coming in through wherever those non-air sealed areas are. And this works to some level. This is way better than natural ventilation, significantly better, but it's got a lot of disadvantages. It's also pretty cheap to do, right? But you might not be getting enough air in the right spaces. You might actually be adding to energy consumption because you're blowing air out of a fan and you're just spending that energy, and you're losing a lot of that energy that's being pushed out of your already conditioned air. You may be pulling in odors from your neighbors. So you depressurize a unit, it doesn't guarantee where that makeup air comes from. It might be next door. It might be outside. It might be the hallway. So you don't know that quality air that's coming back in. It could pull in odors, etc. And of course, it's not balanced, it's not filtered, it's not distributed properly. So there's a lot of negatives, but once again, this is a drastic step up from natural ventilation. Sort of a continuously running exhaust only has a lot of use in our world currently, and it's the least expensive option of all the three that we're talking about. But as you can tell, it doesn't really do the job particularly well. Another disadvantage is that air is coming through all your cracks and seams. Therefore, it's picking up what's ever in those cracks and seams. So that could be pest issues. That could be going through the dirty spaces. That could be picking up, some nasty things on its way into you. And that's what you're intentionally pulling into your house to breathe. You can do exhaust only from a couple different strategies. You can do it centrally, where you kind of have a central corridor running through multiple units. Maybe it's not a single system, but maybe 2 or 3 covering multiple dwelling units at once, where you're pulling air out of these central ducting lines and exhausting them off your roof. That's pretty common. Another one is unitized exhaust, where every single unit has its own exhaust fan. Both of these are options. It really depends on the nature of the building and the layout of the units and availability of chaseways and locations that you can install an exhaust-only system. Sort of how they're connected, how the building is designed is the best determinant here. There's not a huge air quality or indoor air safety or energy difference between the two. Second option is supply only. So supply only does the exact opposite. Instead of pushing air out of the house with a fan, you're pulling air into the house with a fan. Good news here, the air you're pulling in, you can put on a MERV 6 filter, a MERV 9 filter onto that intake, and you can be guaranteed that you are breathing the closest thing you can to good quality fresh outdoor air. So that's nice. It's also relatively inexpensive, just like exhaust. It's a little bit more pricey, but not a lot. You can do a little bit more intentionality of the distribution, right? Your air is coming in exactly where you put that fan, or the end duct, end of the duct line from that fan. And so you can target it and get that distribution. Now, you're still not quite sure where is this air going? Is it really going outside? Or is it maybe going into the hallway and maybe across the hallway into your building mate's house? A slightly different pressure dynamic in their house because they're not pressurizing quite as much. And therefore, or is air coming from your neighbor into your unit because of slight pressure dynamics there that you don't have full control over. And are you breathing, once again, same thing, are you breathing in their tobacco smoke? Are you breathing in the smelling of them cooking fish 24/7? Where's that air coming from? Is it actually getting to the right places? And similarly, the pollutants and the moisture and the toxins you're pushing out, they might just be kind of collecting in places. They're collecting in the cavities and the cracks and the seams, and they're not really going away. They're just maybe going somewhere slightly, so they're and maybe accumulating there in negative ways. And then similarly, you're pushing out, so you're hurting your energy a little bit by ditching some of the quality, the conditioned air that you have in the house without taking some of the energy back out of it. So this works also much better in dry climates. There can be moisture issues with a supply only. And this only works when the spot ventilation is well controlled. That means like your bathroom fans or your hood fans on your kitchens, because introducing those exhaust fans turning on aggressively, that changes the pressure dynamic in one unit relative to the others, which might mean you're no longer actually pressurized and you're just pulling in the air from all of your neighbors temporarily, and not all of it's getting back out of your hood fan from your kitchen range. So I've been leading up to this and maybe have been dismissive in my language of exhaust and supply, but balanced ventilation is really, from an energy standpoint and from an indoor air quality standpoint, it's the best way to go. Balanced units can be just balanced with no heat recovery at all, but ideally you can also add an HRV or an ERV. So a balanced unit just means conceptually that you are pushing air out intentionally and you're pulling air in intentionally, and you're doing those at the same rate at the same time at all times. So your incoming air can be filtered, can be going exactly where you want it to go, and your outgoing air can be actually leaving your apartment, leaving it where you want it to leave, and they're doing it at the same rate, so you're not pushing air in and out unit to unit, and you're not getting as much sharing across the dwelling units, across the apartments in the building. That's balanced. And then with an HRV, a heat recovery ventilator, or an ERV, an energy recovery ventilator, you have the added benefit of maintaining some of the either cooling that you've accomplished in the summer or maintaining some of the heating that you've provided in the winter. And so you're able to salvage some of that waste energy, or that energy that would be leaving the apartment, and reuse it with your fresh air, and that has a big energy value, particularly in colder or hotter climates. And the Northwest certainly counts for that. They're very cost effective. That being said, there is an increased first cost, which we'll get into in a little bit. It does require running some independent ducting. It requires commissioning and some balancing and some thoughtful engineering. With exhaust and supply, there's a little bit of a slap it on the wall, it'll take care of it. With balanced, you have to plan, you have to think it through, you have to follow some good engineering best practices. And that takes thought and experience and a little bit of increased for upfront cost. So a quick little difference between heat recovery and energy recovery. You'll often see them spoken in the same breath or typed with just a slash between them because they essentially do the same thing. Heat recovery lets you take the energy of the incoming of one stream and convert it with the other. So in the winter, let's say, because that's the predominant need in Oregon, you've got your nice, warm, cozy air on the inside, you're pushing it out of your apartment, and it's being replaced by super cold air from the outside. Those two air streams cross, not directly, like there's a heat exchanger in there, so the air streams aren't crossing, so the contaminants are still leaving, but they cross with metal plating between them for that heat recovery, and some of the heat that is flowing out of your house gets dumped into your fresh air coming from inside. And that heat comes through, and therefore you have slightly preheated air, which means your heating system doesn't have to work quite as hard as it would have otherwise. Energy recovery does the exact same thing, but it also captures some of the moisture and therefore the heat embedded in the moisture of that indoor stream. So it pulls some of that out, and that moisture stays in the system and comes back out. And as we know, latent is the term for the heat embedded in moisture within air. That's the latent load. it maintains that latent load. It brings it through, and the sensible energy also gets, and sensible is the term reflecting the amount of energy just in the temperature of the air, that also gets maintained. So energy recovery, a little bit more expensive engineering behind it to do that transfer of the moisture, but you also get more savings because you're saving the heat load that's in there, and you probably also don't necessarily need to run a humidifier on the inside so it doesn't dry out because you're able to keep and maintain some of that moisture indoors. So you can do this through big ducted systems, right? Or that go across the entire building, or you can do this just in unit. There's these package ERVs that just a little mini duct, one unit, you know, in the center of your living room and a little outdoor, and you could put one per unit just doing this work. And the heat exchanger is right in that box, and it does the job that we're talking about. Or they even have these small through the wall models where you don't need any of that ducting, you just plunk it right up against the edge of the wall. And all of that is self-contained in a very simple, straightforward, you know, box. It's pretty easy to install and seal around. The question there is, did you spec it properly for the space and have the running controls to meet the needs of that particular dwelling unit and space? All right, moving on briefly. I guess I'll pause before we go to the next section to see if there's any questions, Mecca, from your monitoring of the GoToMeeting.
I don't see any questions currently, so you can move on.
All righty, thank you so much. All right, so ventilation standards and guides. So you've all been sold entirely, drank the Kool-Aid on the need for good ventilation, the need for balance, the benefit of balanced ventilation, both for indoor air quality and for energy dynamics. And now you want to know what do you need to do this? Well, good news, there's a lot of information out there, a lot of resources to help design proper ventilation and ensure that you're meeting kind of nationally accepted and practiced best standards and codes on indoor ventilation. 4 kind of broad options. The Oregon Code obviously has its own standards. ASHRAE is an institution that helps set ventilation standards and helps give us that information. Building Science Corporation is a great little company based in Boston that is just the leading experts on good quality building science, and Joe Seabrook there has made it a life's mission to push quality ventilation. He's got great guides and great technical information available. And then International Code Council as well also has some information on ventilation standards. So let's start with the Oregon Code. So the ventilation standards for the Oregon Code are dictated by the Oregon Mechanical Specialty Code. And this is based on the 2012 International Mechanical Code. So these codes kind of build up on top of each other, borrow each other's language, sort of a universal expectation. And this is what you have to adhere to when you're doing new construction in Oregon in order to, what are the standards for mechanical ventilation? And then some other guides coming from ASHRAE. So the mechanical code, the Oregon Mechanical Code we just talked about, pretty much just references ASHRAE. It just says, do what ASHRAE says. So it's sort of 3 standards packages within ASHRAE's world that are about ventilation. ASHRAE 62.2 is the standard for multifamily building dwelling units. 62.1 is for multifamily corridors. And these are for typically low rise more than high rise, or the 60s are low rise. ASHRAE 90.1 is standard for high rise multifamily buildings. And there may be a little bit of crossover there where sometimes you'll use a 62.2 standard for dwelling units within a high rise. Depends on the type of system you're trying to put in, but these are kind of these are the Bibles of ventilation standards and strategies. And sort of calculation and specification methodologies. But then you can also get a little bit of guidance beyond those. As I said, Building Science Corporation, their ventilation guide is not written in, it's not written nearly as in code speak. It's much more straightforward, it's much more understandable, and it can really help you teach and help you learn principles behind this and how to specify and install quality ventilation and understand ventilation needs in low-rise multifamily spaces. Highly recommended little guide there. There's also some extra information in the ICC mechanical code that goes a little deeper than ASHRAE. Those are, especially if you're working on high-rise buildings, can start being kind of the tier of engineering support that you may want to consider to do good ventilation systems. So let's talk briefly about dwelling unit ventilation. So depending on which guide you talk about, they're all saying similar methodologies of how to design and specify and install dwelling unit ventilation. First, they each have a different formula for the dwelling unit ventilation rates. How many cubic feet per minute do you need in a space based on its size and its number of occupants? And the good news is that you throw in any given typical apartment, say an 800 square foot 2-bedroom into either of these three formulas, they all spit out pretty much the same answer, right? It's somewhere around 45 to 60 CFM for that apartment. Bigger apartments need more air, more occupants need more air, just a calculation standard to help you guide how many cubic feet per minute that you need there. The next is that they describe the how, that's whether you're going exhaust, supply, or balanced, and the differences between those and how you have to tweak locationally where it goes and the rates themselves depending on your choices there. And then it also talks about controls and ensuring that these controls are operating whenever the spaces are occupied. So this is not spot ventilation, right? This is intentional, continuous, deliberate ventilation. Some of these guides do allow for intermittent, right? Ones that turn on for 4 hours or 2 hours and turn off at other times and take an average over the day. Those are probably on their way out over time, right? It's a much better strategy for indoor air quality and health to just continuously operating fans. And fan energy has gone down and down and down. That's just the direction that the world is going. It's continuously operating. And the only reason you turn off is because no one's home for a big chunk of time, or on some occasions there's some kind of outdoor event where the air quality outside is so bad that you don't want to be sucking that in. So that'll happen when there's a wildfire nearby. That'll happen in certain smog conditions in certain cities. So, but typically it's 24/7, 365 running system of mechanical ventilation, and how you set that up for controls and automation. And then within this, once you've installed, there's also a whole world of kind of confirming and commissioning and testing that these were installed properly. First, of course, is airflow testing. You can put on a flow hood, a few other different airflow testing methodologies, and test that those devices are actually providing the 45 CFM that you calculated is needed for that particular apartment. You also confirm that the filtration system is installed, has the right MERV value on it, and is accessible, and ... And then you also start talking about adjacent spaces and some compartmentalization between your unit and the units next door. There's also some guides on where the intake and the exhaust happen. Mostly speaking about that they're not cannibalizing each other, that your intake air is coming at a location that is free of contaminant sources. That's not right up against, it's not in the garage, for instance. You're not sucking in tailpipe exhaust. That your intake air is coming from a good quality fresh place, and that you're exhausting in the right place as well, where that exhaust air doesn't just get mixed right back into the house. It also pushes that you need to blend spot exhaust in the proper locations, kitchen and bathroom most prominent, so that you can run those beyond your 24/7 mechanical ventilation. You can spot ventilate when you're cooking. So you're pushing out any of the moisture from your cooking, any of the food particulate and contaminants there, or if you're working on gas grills, gas burners, that you're pushing out any of the combustion CO or anything else that's coming off of that, of any incomplete combustion off of that burner. And so there are guides and tables for exactly how this happens and how that exhaust air has to be done in the kitchens and the bathrooms and the toilet rooms, of the size of it and intermittent versus continuous. And these are the guides that exist within ASHRAE and these other guides that I've talked about. Of particular, kitchen hood needs a minimum of 100 CFM available, and bathroom fans need a minimum of 50 CFM and 25 continuous. So in the bathroom, when you take a shower, you flash it on to 50 CFM to flood out all of that moist shower air out of the bathroom. So next section, I'll take a pause as well on sort of those standards and guides and engineering principles before I go on to the next section. And Mecca, go back to you if there are any questions that I can address now.
Let's see, we don't have any questions currently, but I'll just remind the audience that if you do have any questions, you can enter them into the question box, and also at the end, we can unmute you if you have any questions and you can raise your hand.
All right, thanks, Mecca. So now that you've learned about the reasons for ventilation and the methodologies and the standards and guides behind it, let's talk about kind of the business case for choosing which system and prioritizing good ventilation in the buildings you're supporting or building or working on. So odor control. My brother lived in a multifamily building where his downstairs neighbor cooked fish for breakfast and dinner pretty much every single day, and he broke his lease almost entirely because of that situation. Odors crossing in a multifamily building can be pretty powerful and pretty life-changing. They really impact you. So good ventilation prevents odors crossing the borders. Good compartmentalization of each unit and good ventilation just flushes that out and keeps it inside. And that can be done with both spot ventilation and whole unit ventilation. But ideally, as I said before, whole unit ventilation is part of the package there for sure. And this can also be done by compartmentalized air sealing, plus these balanced ventilation options, and as an ideal, as a first pass, or as a backup pass, positive pressure ventilation is better for odor control than negative. Positive pressure being that I am supplying air into my dwelling unit, not that I'm evacuating air from it with an exhaust only. And a positive pressure running continuously, if you keep your unit positively pressured, that means it's less likely that a neighboring odor or smoke can sneak into your dwelling unit. However, it's not a guarantee. Balanced is still the stronger way to actually accomplish this. So with odor control, within a balanced ventilation system, each unit is compartmentalized. Your fresh air is coming in where you want it from the outside, and your stale and maybe fish smelly air or smoke smelly air is being pushed out exactly where you mean it, and it's not crossing into the hallway. It's not crossing into your neighbors. Big value there. In supply only, you still have the chance of that sort of a little bit of crossover between the units because of slight imbalances between how positively pressured each unit is, as well as what's going on in the hallway. Let's talk about moisture control. So here's the other big reason that your multifamily buildings will need ventilation is moisture control. So reduce comfort complaints, reduce the chances of building rot, and reduce instances of mold and mildew. So humidity on the inside has a big impact on our comfort indoors, right? Different temperatures feel differently with the various relative humidity. You get really low humidity, you get those chapped lips, you start feeling dry in your mouth. That's a nasty discomfort that can really impact the way that you feel about your day and your life. Moisture also can accumulate in the building to cause building rot. And when moisture is in the building and accumulates in the building, you might get molds and mildews, and those can have very big impacts on respiratory health and human health. So once again, the best way to do this is a balanced system, with either HRV or ERV, separate supply fans and exhaust fans, keeping the moisture out. These are the kind of the controlling methodologies that you want to deal with relative humidity in the house. Along those lines, so the chart you're looking at is you have relative humidity going from low humidity on the left to high humidity on the right. And each of the rows is a different indoor air quality issue. Bacteria, viruses, fungi, mites, respiratory infections, allergic rhinitis and asthma, chemical interactions, ozone production, boom, boom. And you can see that as you get to the extremes of low humidity and to the extremes of high humidity, your risk factor, as demonstrated by those colored triangles, gets higher and higher and higher. And there's kind of this nice little optimized zone in the high 30s, low 40s, maybe up to 55, where you have the lowest incidence of the most dangerous indoor air quality issues that come from moisture. And then secondarily, the backup to this is that unmanaged moisture, as I said, can lead to huge building durability issues. And these are huge costs on the building owner or on the tenants. So that rot and repairing rot, major cost. Meanwhile, there's been a human cost the entire time with molds and mildews and these other aspects. So very significant impact to both the bottom dollar and the health of occupants based on moisture control. So another aspect of the business case is thinking about the cost to operate these systems. So there's a cost to heating or cooling and dehumidify fresh air. So obviously with an ERV or an HRV, that cost goes down because you're recapturing some of the energy that you would have been expelling and reusing it while still getting rid of the toxins and the moisture and the bad stuff that you don't want. So there's a value there to balance systems with HRV or ERV. And then of course there's the cost of the fan energy itself. So the fan is running perpetually typically or preferably, and that costs a little bit of energy. Now, as I said before, some of the newest fans are very low energy, running continuously with very low sound issues, and really aren't nearly the energy penalty that they were even 5 to 6 years ago. This industry in this world has grown up has matured very quickly as the build tight, ventilate right statute has been put forth. The Panasonics of the world and the air cyclers of the world have really caught up technology-wise to provide quality fans that do this at low energy and low sound. So just a quick little comparison of the cost of operating. It is a little bit more expensive to operate an exhaust only than it is to operate a balance. So the continuous operating costs. And that's because with the balance fan, you have exact control of the airflow and of the ducting and of the pressure dynamics. With an exhaust only fan, you don't. So you have to kind of goose it a little bit harder, and you may have to go through a longer duct run to get that air out. And so your cost estimates for on the left here is a standalone HRV, and on the right here is a exhaust only system that uses smart exhaust, which is a proprietary technology of this company, Air Cycler, that turns it on and off at certain times depending on indoor conditions. So, you know, even then, that's going to be a pretty high end. You can see that operating cost per month, you're saving about 25% possibly by going with a balance system, just on that operating cost of the fan. And then you have maintenance considerations. So when you have a staffed building that has a maintenance staff, so larger buildings, larger complexes where there's a maintenance team, central systems are probably pretty good because that maintenance team can change the filters, can make sure that it's operating, can manage. So central systems and positive pressure central systems, those can be strongest with a staffed building. With an unstaffed building, you're probably thinking more towards in-unit exhaust, or even better, in-unit HRVs, so those wall pass-throughs, or those sort of mini package ducted HRVs. In that case, then it requires some tenant education to let them know what the system is, why it's on all the time, and when they need to change their filter, and on what schedule and what filter they need there. So there's a little bit of tenant education there, but can and should be done. So let's talk briefly about first cost now of installing. We talked about kind of ongoing costs and the maintenance costs, but first cost. So this chart kind of shows 4 different strategies, and that little middle column is the approximate installed first cost per dwelling unit. Obviously, this varies greatly building to building, depending on the size of the units and the complexity of the shell and where the duct chases can go and what the design specs are. But you can kind of see this as a initial, at least order of magnitude concept here. So, these are relative and not absolute. So as you can see that, yes, the distributed HRV, ERV is the highest first cost. That's made up by the operating cost long-term pretty considerably, particularly getting the heat recovery aspect or the energy recovery aspect of that unit over time. So these first costs are reduced, typically the lifetime costs of these systems are less expensive than the of balanced systems, balanced HRVs, are significantly less expensive than exhaust only or supply only. But you could also see that in some cases, these local ERVs, the sort of packaged through the walls just for a unit, the first cost can be right in line on the similar order of magnitude as exhaust only. A little bit more engineering because you have a heat exchanger on the inside of the package, and you have, but it's not that much more, and those costs are coming down as well. So those can be a great opportunity. And so coming from the Oregon Multifamily Energy Program team, these are our blue ribbon prizes. I've betrayed all of my biases in the process of giving this webinar. Balanced ducted systems with HRV or ERV is by far the first choice for indoor air quality and for energy. They do there's a little bit of a first cost hiccup there that can be tough to stomach. Luckily, incentive programs like the Multifamily Energy Program is there to help support some of the install costs of these and help get some of the money back by putting in such quality systems. But those really have the best lifetime air quality and cost and energy dynamics of the options. Second choice, other balanced systems, or possibly exhaust with a constant flow, and making sure that you are installing those with energy efficient fans and proper considerations of static pressure loss if they're ducted, really engineering them appropriately and having a constant flow. So that is my presentation on ventilation. Thank you so much for listening, and I'm going to turn it back to Mecca to see if there's any questions. We have about 10 minutes left in the hour.
All right, thanks, Matt. Just as a reminder, if you have any questions, you can enter it into the chat box or raise your hand and we can unmute you. We did have a couple of questions come through. One of them was on what is the typical cost for ERV and HRV per unit, and you covered that in your presentation.
That may have been answered in the second to last slides.
Yep.
in that ballpark.
And that was a question from Scott, who has raised his hand. So I will unmute you, Scott, and you can follow up. So Scott, you are now.
Oh, it's okay. Can you hear me?
Yes, we can hear you, Scott.
Dang. No, that answered my question. But second question was, what kind of space heating can you add with these?
All the usual suspects. So they're independent of the space heating choice, whether you're going, a gas furnace or a heat pump, or it's as well as which distribution strategy. You can do. There are ERVs and HRVs that are centrally integrated that will go through a sort of central ducted system. If you're using a distribution strategy that has sort of whole building ducts or whole unit ducts, you can kind of integrate an ERV, HRV into that directly. That gets you pretty up into the sort of the primo engineering decisions of specifying that and designing for it. But it can be a great option, particularly in new construction.
And we see a lot of resistance heat in these kind of buildings.
Yeah.
So it still works with like Cove.
I mean, the heat recovery aspect of it can work with electric resistance. Obviously, us as an energy efficiency program, we're pretty, get rid of electric resistance where you can. It is by far the most energy intensive heating methodology there that is possible. But we also know that some buildings, there's only so much you can do, and that electric resistance has its place in certain situations, like maybe hallways or common area rooms that aren't used as frequently. But yeah, but in terms of the HRV functionality or the ERV functionality, it doesn't know what the heating system that's going on in the building. It has no,
Okay.
they're not connected unless they're intentionally connected through ducts, and it's indifferent to that choice.
Thank you.
Okay, thank you, Scott. All right, we do have another question that came through our chat box, and it was on the section on in-unit HRVs and ERVs. And the question was, for through-wall HRVs, would additional measures need to be taken to ensure proper air distribution for the other rooms within the unit?
Yeah, so that was that photo of the sort of the through-the-wall ERVs or the packaged ERVs. And yes, once again, those are decisions that need to be made thoughtful to the space that it's supplying. And a wall-mounted ERV, you need to make sure that if the apartment is kind of deep and vacuous and has many, many rooms, it might be difficult for your, for that air to circulate properly through that HRV. And you might get stale air in the far corners. So you'll need to do things like, cutbacks underneath the doors to make sure that air is able to circulate below them, or just sort of think through your space. For a studio apartment or a small one-bedroom, you're fine. That's easy. That's a no-brainer. For deeper systems, you may need a second ERV somewhere else, or a second, or something that's ducted to get out of that space rather than a through the wall, that you can get that distribution.
Okay, great. Thanks, Matt. So I don't see any other questions. I'll just pause to see if any other come through with a couple of reminders. So this session is being recorded, and we will post that recording and the slides on the program website. And also keep a lookout for our upcoming trainings and register for them through our website. Okay. Don't see any.
I'll give a quick shout out and a thank you to Carrie B, who helped develop a bunch of these slides, as did Dan Wildenhouse and Steph Berkland's support and Marion Gobus' support on indoor air quality and multifamily. There's a sort of a deep bench of experts within TRC's group supporting the Oregon Multifamily Energy Program that can help you with these decisions and these choices and understanding these systems. So please, if you have follow-up questions, just come to the team and we'll help you understand what the options are and how to make the right choices.
Great, thank you, Matt. So we will end the webinar there, and thank you all for joining us, and have a great day.
Thank you.